Good morning students. We'll continue again with unit number 4 and topic number 4, which is importance of sediment transport, design of stable channels in India and design of alluvial canals using Kennedy's and Lacey's sill theories. Importance of sediment transport. What is sediment transport? Whenever water flows in a channel, be it natural or artificial, it tries to scour its surface. Silt or gravel or even larger boulders are detached from the bed or sides of the channel. These detached particles are swept downstream by the moving water, and this phenomenon is known as sediment transport. The importance of sediment transport. The first one is the phenomenon of sediment transport causes large-scale scouring and siltation of irrigation canals, thereby increasing their maintenance. Many poorly designed artificial channels get silted up so badly that they soon become inoperable, causing huge economic loss to the public exchequer. The artificial channel should therefore be properly designed and should not fail to carry the sediment load admitted at the canal headworks. The second point is the design and execution of a flood control scheme is chiefly governed by the peak flood levels, which in turn depends upon the scour and deposition of sediment. Firstly, the bed levels may change by direct scouring or deposition of sediment and thereby changing the flood levels. Secondly, the scouring and silting on the river banks may create sharp and irregular curves which increase the flow resistance of the channel and thereby raising the flood levels for the same discharge. The third point is silting of reservoirs and rivers is another important aspect of sediment transport. The storage capacity of the reservoir is reduced by its silting, thereby reducing its use and life. Nature rivers used for navigation are frequently silted up, reducing the clear depth or draft required for navigation. Sediment deposited in these rivers and harbors may often require costly dredgings. Sediment transport thus poses numerous problems and is a subject of great importance and possesses enough potential for further research and development. Next, sediment load. The sediment in a canal is a burden to be borne by the flowing water and is therefore designated as sediment load. Bed load and suspended load. The sediment may move in water either as bed load or as suspended load. Bed load is that in which the sediment moves along the bed with occasional jumps into the channel, while the suspended load is the one in which the material is maintained in suspension due to the turbulence of the flowing water. Next, bed formation. In view of practical aspect, the channel bed may be distorted into various shapes by the moving water depending upon the discharge or the velocity of the water. At low velocities, the bed does not move at all, but it goes on assuming different shapes as the velocity increases. Let us see what happens to a channel bed made of fine sand lesser than 2 mm diameter when the velocity is gradually increased in steps. Next, design of stable channels in India. So long as the average shear stress acting on the boundary of an alluvial channel is less than the critical shear stress, the channel shape remains unchanged and hence the channel can be considered of rigid boundary. The resistance equations such as those given by Chassis formula and Manning's formula remain well applicable to such channels. However, as soon as the sediment movement starts, undulations develop on the bed which increases the boundary resistance of the channel. Besides this, some energy is required to move the grains. The suspended load carried due to the turbulence in the flow further affects the resistance of the alluvial streams, and all these factors render the evaluation of resistance of alluvial streams to be a very complex problem, and the complexity further increases if one includes the effects of the channel shape, non-uniformity of sediment size, discharge variation and other such factors. None of the resistance equations developed so far takes all these factors into account. The direct occurrent mathematical solution to the design of channels in alluvial soils is therefore not an easy job, and hence in India, alluvial channels are designed on the basis of hypothetical theories given by Kennedy and Lacey. These theories are based on experiments and experience gained on the existing channels over the past many years. The semi-theoretical approach discussed in the previous article is however used to design channels in countries like America and Europe. Problem in India. So in prehistoric periods, the area bounded by Indo-Gangetic Plain, that is, the area starting from Himalayas to Vindhya Mountains, used to be in the form of depressions with water flowing over it. But with the passage of time, it was filled up with loosely filled fine silt particles, thereby forming nothing but what is known as alluvial soil. Almost all the North Indian rivers flow through such soils and therefore do carry a certain amount of sediment. Artificial channels have to carry their water supply from such rivers and thus carrying sediment. We also know that water moving with a given velocity and a certain depth can carry in suspension only a certain amount of silt of a certain nature. If water of a given velocity and depth is not fully charged with silt that it can carry in suspension, it will scour the bed and sides of the channel till it is fully charged with silt. Hence, if the velocity of flow in the channel is more, the bed and the banks are likely to be eroded, and similarly if the velocity is less, the silt which was formerly carried in suspension is likely to be dropped. Silting and scouring in channels is not very uncommon and is understandable, but must be avoided by proper designs. Scouring lowers the full supply level and causes loss of common. It may also cause breaching of canal banks and failure of foundations of irrigation structures. Silting interferes with the proper working of a channel as the channel section gets reduced by siltation, thereby reducing the discharging capacity of the channel. Therefore, while thinking to design a properly functioning channel, one must think to design such a channel in which neither silting nor scouring takes place. Such channels are known as stable channels or regime channels. Next, what is a regime channel? A channel is said to be in the state of regime if the flow is such that silting and scouring need no special attention. Such a state is not easily possible in rivers, but in artificial channels, such a state can be obtained by properly designing the channel. So the basis for designing such an ideal non-silting, non-scouring channel is that whatever silt has entered the channel at its head is kept in suspension so that it does not settle down and deposit at any point of the channel. Moreover, the velocity of the water should be such that it does not produce local silt by erosion of channel bed and slopes. Design of alluvial canals, Kennedy's and Lacey's silt theories. An alluvial channel is defined as a channel in which the flow transports sediment having the same characteristics as that of the material in the channel bottom. In the case of alluvial channels, the channel surface consists of alluvial soil which can be easily scoured. Moreover, the velocity is low which encourages silting. Therefore, in an alluvial channel, both scouring and silting may occur if the channel is not properly designed. The quantity of silt transported by water in alluvial channel varies from section to section due to scouring of bed and sides as well as due to silting or deposition. If the velocity is too high, scouring may occur. On the other hand, if the velocity is too low, silting may occur. The common area of an irrigation channel decreases if the scouring occurs because the full supply level falls. The discharge capacities decrease if the silting occurs because the reduction in cross-sectional area. Therefore, the alluvial channel should be designed such that neither scouring nor silting occurs. The velocity at which this condition occurs is called the critical velocity. Such an alluvial channel is called a stable channel. A stable channel is one in which banks and bed are not scoured and also in which no silting occurs. Even if there is some minor scouring and silting, the bed and banks of a stable channel remain more or less unaltered over a long period of time. So this is your assignment for lecture number 27. The question is you have to write in detail about the Annaram barrage of India. I repeat, you have to write in detail about the Annaram barrage of India. The last date of submission is given here. Now we'll go through a video and also you can write down your attendance in the chat box now. That's all for this lecture. Thank you.
There is groundbreaking reform taking place in the Australian irrigation industry as the nation battles severe drought, the growing problem of water scarcity, and the effects of global warming. The government is responding with a major drive to modernize its irrigation supply infrastructure and improve efficiency.
This is the start of the state government's $1 billion project to upgrade irrigation in the state's north and produce more water for Melbourne.
There is a ton of water which is being lost. We want to capture that by investment and improving it.
It's an upgrade that many local irrigators believe is long overdue.
Rubicon's Total Channel Control Technology, or TCC, is central to the automation of the channel networks. TCC is gaining recognition worldwide as a major advance in the efficient operation of open channel networks, resulting in significant water savings and improved services to farmers. Much of the technical breakthroughs Rubicon has achieved in the development of the TCC solution are the result of a strong research program run in collaboration with the University of Melbourne. A staggering 70% of the world's available water resource is used for irrigation, supplied by thousands of miles of channel systems where operating practices have remained largely unaltered for centuries, limited by manual operation and poor flow measurement. With the efficiencies of these systems typically ranging from 40 to 70%, it is easy to see the huge potential areas to generate new sources of water. To date, TCC is achieving efficiency improvements in the order of 20%, which in turn is generating significant quantities of new water for urban, environmental, or further irrigation uses. Total channel control involves retrofitting Rubicon's flume gates to existing regulating structures, enabling accurate flow and water level measurement at each structure, as well as optimal control. The flume gate is a unique product incorporating precision and specialized instrumentation with over 4,000 already sold worldwide. It's designed to be easily fitted to existing structures and to cope with the harsh operating environment experienced in the irrigation industry. The flume gate also replaces the aging devices that are used to meter water onto the farm. Over 10,000 flume gates will be installed as part of the $1 billion modernization project on 6,000 kilometers of channels in the Goulburn-Murray district. The project will achieve significant savings through accurate metering, halting outfalls that occur with manual operation, and pinpointing leakage and seepage hotspots using the TCC loss detection system. These three factors are the major causes of loss in channel networks. With TCC implementation in the Colliambally irrigation area almost complete, a remarkable system efficiency of 90% has already been achieved, a world benchmark for gravity channel systems. Not many pipe networks can achieve this efficiency, let alone open channel networks.
It takes effectively 7 days for water release from the dam to get to our river offtake, but through TCC and the systems that we're implementing, it'll allow us to provide near on-demand water for our customers who are ordering. So, no, we're not talking days, and 2 hours is what we believe we can deliver a service. So if you go and order water now, in 2 hours' time you can expect it delivered to your farm gate.
Total channel control comprises sophisticated real-time computer and communication systems, as well as modeling and control software that manages vast channel networks. The secure and robust communications, or SCADA systems, being engineered by Rubicon are some of the largest of their type in the world. The powerful TCC software is an integrated SCADA, planning and scheduling, modeling and control system that has taken many man-years to develop. The software provides a seamless interface between the farmer ordering water through to the control system that can deliver the water to the farm within 1 hour's notice. The TCC system is fully automated, with human intervention only required to address any problems that are identified by the comprehensive diagnostic system. As well as the on-demand supply service TCC delivers, there are also significant additional benefits to the farmer. Rubicon's Farm Connect software exploits the communications and computing infrastructure of TCC to provide irrigation scheduling and automation tools that assist the on-farm operations. Farmers can now track their soil moisture and apply the water in an efficient and timely manner. TCC is equipping the farmer with the necessary science and tools to achieve the levels of food production sought from the next generation of agriculture around the globe. Rubicon, leading the world in the modernization of irrigation channel infrastructure.
Rural water supply is about getting the right amount to the right place at the right time. It sounds simple, but with canals, it's a